Next, we have provably secure onion routing against a global adversary. So Tor, watch out. Philip's going to present as soon as the slides appear. All right,
Perfect.
go ahead.
Hello. Thanks for the introduction. I'm Philip Scherer from KIT, and I'm presenting to you today a framework for provably secure onion routing against a global adversary, a joint effort with my co-authors Christiane Weiss and Thorsten Struve. Now, before we start, let me just add one little note on the. So there's a bit of sort of conflation in the literature on the terms onion routing and mixing. And so I'm going to try, for clarity, to use the term mixing throughout this talk, but know that as soon as you go into the literature, you'll be seeing these terms pop up simultaneously, sometimes meaning the same thing, sometimes meaning different things. It can get a little confusing. So anyway, let's talk about mixing. So mixing is a widespread technique for implementing anonymous communication. Basic idea being that if you have multiple senders like Alice and Carol trying to message multiple receivers like Bob and Dave, they'll each pick a path through the network featuring multiple relays. In this image, the adversarial relays are shown in red, while honest relays are shown in black. And the point is that if two paths cross at an honest relay, then the adversary won't be able to link the outgoing packets to the incoming packets, which breaks the link between senders and receivers. Note that this is the free routing construction, where essentially every paths are freely chosen through the network. There's another way to construct this stuff, which is layered or cascading networks, where we have explicit layers. That's separate from this, but so we're looking into mixing specifically in free routing schemes, and there are a lot of these. And there's a basic structure that looks like this. It's consistent across basically all of these schemes and lots of formalizations, but the devil is in the details. And the problem is there are a lot of minor variations on the idea. And this turns into an issue when you actually try to use one of these schemes or analyze one, because it's very easy to accidentally violate an assumption or use something in the wrong model, and then everything falls apart, which has also happened in the past. So what our goal is to unify all of these different variations into one framework that makes them explicit, so we can actually systematize the differences between these different schemes, frameworks, variants, and in addition, we also aim to provide a formalization for provable security for all of these variants. We identify 4 options when we look at these variants where they differ. They come together into the stir model because I prefer my packets stirred, not mixed. These options are binary, so there's 2 options for each, and they correspond to the letters of the acronym. So we have, first of all, the type of service that these variants offer. Then we have whether the variant places trust in receivers, so whether honest senders only ever message honest receivers. Then we have the type of payload integrity in the scheme, and finally we have whether the scheme supports replies or not. The T and the R are fairly self-explanatory, but S and I warrant a little more explanation, so let's get into those. So the type of service refers specifically to the way the network itself is constructed. There are 2 basic ways to do this. One is the integrated system model, where we have receivers that are themselves part of the network. So the receiver, Bob here, is himself also a relay in the mixed network. On the other hand, in the service model, Bob is not part of the mixed network. Bob probably knows nothing about mixes. Is just a web server. And instead, the final relay is responsible for coordinating the communication between Bob and the mixes. Seems like a minor detail, but this is exactly one of the ones that becomes so crucial, as we'll see in a little bit. And on payload integrity, we have 2 different variations on this too. The first is hop-by-hop integrity. So here the payload, which contains the actual message we're trying to communicate, is integrity checked at every relay. And so if an adversary tries to modify the payload, then that will be discovered at the next honest relay, which will, in most cases, discard the packet. And on the other hand, in some schemes, we have end-to-end integrity, where instead a modification will be discovered at the very last relay, the final one, and will be dropped there. Note that this is only applicable to payloads. In every scheme and every formalization in the literature, the routing information has hop-by-hop integrity. So you can't send packets going haywire through the network. So we have our model, our framework. Let's try to categorize the related work, because that was the whole point. We have 16 variants in total, because that's 2 to the power of 4. And we categorize both packet formats and formalizations we find in the literature. We refer to our different variants using the letters of the stir model, where the letter itself stands for basically the positive version, and the letter with the negation bar on top stands for the negated version of that option. So I've just brought a couple examples here. The real table is very large. So for example, here we have the variant in the integrated system model with untrusted receivers, hop-by-hop integrity, and no replies. For example, this applies to the mixed master scheme. And here I also have a little diagram so you can see what the network looks like and how a modification by the adversary would propagate through the network. Next, we might consider a variant in the service model with replies. So for example, this would be like Mixminion, Babel fall into this variant. So now we can see Bob is outside of the network. Or we might have a variant with end-to-end integrity, like for example for Sphinx and Minx, this is the case, where packets are dropped at the final relay if they're modified. So we were looking at all of these variants and analyzed them a little more closely. And we made an interesting discovery, which is that 2 of these variants are generally vulnerable to tagging attacks from global adversaries, like by their construction. This applies to integrated system variants with untrusted receivers and end-to-end integrity. The way it works is that the adversary can modify, i.e. tag, the payload as it leaves the sender. That tag will then propagate through the entire path and will then fail the integrity check at the final relay. Now, since we have untrusted receivers and an integrated system model, that final relay is the receiver and might be adversarial. And so the adversary could notice that this links the sender to the receiver, which is exactly what we were trying to prevent. This vulnerability affects every scheme in these variants, which includes, for example, CHOM mixes and the setup phases of Hornet and Taronet. Okay, so we've found that 2 of these variants are vulnerable in a certain sense, and we've constructed the model itself. Now we move on to our second goal, which was the formalization. The status quo for formalizations for provable security in these variants is that there are a couple. There are formalizations for 4 of the 16 variants. They're listed up here. Note that the most common variant, the one with the largest number of schemes in it, is without formalization. And in addition, the existing work builds on top of each other. So even if you try to use one formalization from a specific work, you'll typically be forced to also look at the work that came after it, because while that work transposed it into a different variant, it also fixed issues in the previous work. And so you'll have to backport fixes if you want to do it right, and it becomes a whole mess. So what we do is provide a new theoretical foundation for provable security in all of the variants. We base it on Kuhn et al.'s onion properties. So what that nets you is 3 game-based properties in every variant. And if, for example, you're designing a scheme or you're looking at an existing scheme, you just have to verify that it satisfies these 3 game-based properties. And with that, we have a generic proof that will show you that with those 3 properties, you also imply an ideal functionality that describes the basic functionality in that variant. So that, which you can then use to abstract how the mixing variant actually works. The properties and the ideal functionality are parameterized, so if you want to use them, Basically, all you got to do is figure out which variant you're interested in, plug it in, and then the correct formalization will just drop out of that. So in summary, we propose the STIR model, which encompasses 16 different variants of mixing based on 4 binary options. These are the type of service, the receiver, the trust placed in receivers, the integrity of payloads, and whether replies are supported or not. We use that model to categorize the existing work on mixed formats and formalizations. And in doing so, we discover a general vulnerability in a variant used by several formats. And in addition, we formalize provably secure packet formats in all of the variants with a parameterized framework based on these game-based onion properties and an ideal functionality. So if you're still interested, then I welcome you to check out our paper. And yeah, thanks for listening. I'll take any and all questions.
Thank you, speaker. We have time for questions. Anyone have a question? Down in the front? Should I? Let's race.
So, Rob is pretty fast, huh? Thanks, Philip, for the talk. Just short clarification and then a follow-up. You're using a global passive adversary who also locally corrupts some of the receivers or relays, right?
So in general, like in the formalization, we assume a globally potentially active adversary, but like the tagging attack, for instance, that we introduce here, also works for a globally passive adversary that's locally active. So like this applies anyway. The formalization is strong. I mean, it's even stronger in general, but also like can be used in that scenario.
Okay, great. Follow-up question to this is, for global passive adversary, you would need actual mixing, but you're only focusing on the formats.
Yes. Oh, yeah. I think I forgot to mention that at some point. We're mainly focusing on packet formats. The like replay attacks, timing attacks, and stuff are on the protocol level, which is one level above where this work sits at.
I would think it might be interesting to at some point extend that to this level.
Yes, it is, of course, promising future work.
Okay, great. Thank you.
Other questions? Okay, then I'll ask one more. Where do you go from here? Are you going to write 16 papers now, or do you have other plans?
No, well, the point was that we don't have to write 16 papers, right?
Well, you have to build each of the designs.
I'd recommend actually looking into the paper. We do this fun thing with the parameterization, so there's actually only one design. Yeah, but yeah, from here on out, it would be interesting to look into exactly the protocol level, so taking it one step higher, or also going into, I mentioned earlier, the free routing versus layered approach, and taking this into layered networks, where we have some more specific constraints on how the routing occurs would also be interesting.
Okay, thank you. Let's thank the speaker again.